But of course, networks are not very simple like that. You have this huge metabolic pathway, and here it's very summarized. So, but the thing is, metabolism operates as highly integrated network. So everything here is connected. Okay, if you have more sugars coming in, you're gonna change everything in your body. So, as I was saying in the last class, it does not matter how much you eat, but how much you burn. Because Olympic athletes, for example, Michael Phelps, he was eating 1 kilograms of pasta in a lunch and 12 hot dogs in the breakfast. So this is insane. He's taking carbohydrate like hell, but he's burning this because he's an Olympic athlete. So the amount of food, the amount of carbohydrate entering in his body, it's a lot, but he's using it to produce energy and he's burning it. Okay? So if you do that and you do not burn the carbohydrate, instead of producing energy, is going to produce lipids, fatty acids. So you are going to get fat. So don't do that unless you are going to run 30 kilometers per day. So what is different from uh, the way we see uh, metabolism as network change completely the paradigm of biochemistry reactions, for example, because we are used to have in the books the pathways. For example, you have glucose, you have sucrose being degraded to glucose, glucose to glucose 6-phosphate, glucose 6-phosphate to glucose 1-phosphate, fructose 6-phosphate, and so on. So here you have the pathway. This this is not wrong. These reactions can really work on this direction. I'm not saying that it's wrong, but it's this kind of view of the metabolism give, provides impression that it's too simple, right? Because it's linear. The information is coming from sucrose and go to glucose 1-phosphate, and that's it. Yeah. But the thing is not simple like that. In a network, you have you can have the carbon going from glucose or the circle, yellow circle to the blue one. You can, the information can go. But the thing is, you have many interactions between these metabolites and the enzymes. So you have allosteric regulation. You have some metabolites that are more related to the signaling. For example, fructose to 6B, fructose to 6-bisphosphate. It's a signaling metabolite. And you have also, for example, exokinase is a very important enzyme for signaling, to provide a signal about sugar levels. So more than enzymes and metabolites, we have signaling things behind, which are not really, you cannot really understand looking to a linear pathway like that. So this is better visualized by putting these informations in a network. Okay, this is something that the network can provide more than the pathway view. But the thing is, where this information comes from? The origin is artificial neural networks. So these are computational systems based on the human nervous system. So take a look in this figure. You have the input layer, layer 1, layer 2, and the output layer. So think that input layer are genes, are proteins, and so on, metabolites. And then you have the output layers, which could be other genes, other proteins, or other metabolites. So given that this class is about metabolic network, let's think about in a metabolic network. So the input layer would be some metabolites. The links between these layers are the enzymes. So you have more than one enzyme that can interfere in the level of the layer 1 or in the layer 2 and the output layer. So it means that for these three output metabolites here, you can have many different pathways. Okay, perhaps you have in the input layer the first cycle, and then you can have the first or the second or the third or the fourth or the fifth cycle of the layer 1, and then in the layer 2 also. So you are amplifying the response and you are increasing the complexity that the information from the input layer is getting to the output layer. So this is basically how our neural systems work, and the physics has copied this and integrated this, for example, for computer networks, and then this is now transformed into biological networks. So how? The mathematicians are transforming this information into mathematical questions. Mathematical equations. So if you have the interaction between the first circle x with one of the cycles of the hiding layer, and then you have the output layer. So every interaction here, you can measure this interaction. For example, if you have two metabolites, you can measure the interaction between them by doing some correlation analysis. So you have a signal, you have a strength of this correlation. So then you start to create the networks and build these very complex networks. So we are going to do that in the next class. But some concepts are very simple about networks. The networks can be directed or undirected. This is a typical this is a typical directed networks. So it's the same example, but now we have switch instead. The links we have arrows. You see? So the degree of connection of the node A has changed because you have connections that are in and out of the node A. For example, the nodes B, C, D, and E are directed to A, and A is directed to G. Okay, so what kind of biological information we have from this? Directed networks are, for example, if you have B activating A or C activating A, and then you have this kind of interaction. For example, in this case here, A is activated by B, C, D, and E, and is activating G. A activate G, then you have an arrow from A to G. Okay, this is directed networks. But let's have a look in some examples, real examples. This is, sorry, this is too simple. This is just to give you the theory, but the reality is. So these are real networks, okay? So at the left you have a protein-protein interaction network from yeast, and at the right you have a gene expression network from, I guess it's, I don't remember which organism is this. So you can, if you want, you can check in this paper. I guess it's also yeast, I'm not sure. Anyway, so in the left side, you have protein-protein interactions network, which means that one protein interacts to each other, to interact to another protein, and that's it. So undirected networks, we are not saying anything about for example, if this protein inhibit or activate the other protein. No, they interact to each other and that's it. So in this case, you have a link when two proteins interact to each other. If they don't interact, then you have no link. You have no link. Okay, undirected networks, it's mainly, not only, but mainly protein-protein interaction networks. So I'm just giving two examples here. So, okay, there are many other examples of directed and undirected. For example, in this paper, Pala et al., you can check many kind of directed networks. So it's a very interesting paper. So gene expression networks, you have arrows. You have arrows from one node to another. So it means that this gene is regulating the gene that the arrow is going. So you have a direction between the nodes of the network. And just have a look on these two networks. You can see some important information. For example, there are some nodes, for example, the CBF1 node of the right network, it's highly connected nodes. And you also have, for example, I think it's STC12, DIG1. So in this, what else? So many other nodes are highly connected nodes.